Hi everybody, welcome back to Chem 140. We're going to be doing Unit 6 today. Maya is here. She immediately wants to say hello. Oh, she's running away. Never mind. Oh, no, now she's coming back. Yeah, she can say hi. Come here. Come say hi. Yeah, what are they going to learn today? Yeah, you don't know either, huh? That's okay. Maya says hello. And yeah, oops, I hit the wrong button here. Alright, Unit 6 starts with just sort of a little portent, I guess we'll say. In Chapter 9, we're going to be using this list of ions called the polyatomic ions. I have this list here for my in-person classes because I want students to memorize these because you use them so often. It's just having them on the top of your tip of your tongue, I guess is the expression I'm looking for. Is very important in order to be able to quickly answer questions. Since this is an online class, you can just reference these polyatomic ions from this documentation whenever you need to. So remember that's here. It's at the start of Unit 6. We're not going to touch them until Unit 9. And then Unit 11 is when we're going to use them a lot. That's the naming unit, when we're going to describe the nomenclature of various ionic compounds, and these ions will show up. There is a text online. I want you to use this specific list that I'm giving you because this is the one for Chem 161. If you know these polyatomic ions by memory, then you will be all set. This is page 1 of 2, so there's page 2. A polyatomic ion is a collection of atoms as well as the charge on it. So, for example, acetate up here is not just C2H3O2, but it is also this minus, so don't forget the minus up there. Okay, so all polyatomic ions have a charge and a formula and a name, and you need to be able to connect all three parts together. All right, that's going to be important for you later on. You can pause the video and copy these down or print screen or whatever. Let me get rid of this ink. There we go. And then here's page 2. And yeah, so on this slide over here, I have some tips for memorizing them. You can review those on your own time. Students tell me to do flashcards. There are online Quizlets and flashcards that you can do if people find them and find one that they like. Post it in the Discord and let other people know. Really just spending time learning these and doing something will get you most of the way there. And again, this is an online class, so it's not super crucial that you commit them all to memory right now. Just do enough practice with them and eventually you'll remember them. Yep, here's page 2. Sorry about that. You get print screen. Grab your camera, pause the video, that sort of thing. There you go. Cool. All right. Unit 6, not very much to talk about today. We're going to talk about matter. Why does matter matter? In a chemistry class, matter matters a lot because that's the whole point. The interaction of any pieces of matter with each other to transform and turn into different matter is what we call chemistry. That's the whole point of taking this class. So first of all, we have to define matter. Matter is going to be any object that occupies both space and also has a mass associated with it. Now, depending on the phase that you are considering, the matter will have a different molecular arrangement. We're going to talk about that a little bit more later. But all we care about is that there are atoms and stuff in a region of space, and that stuff is matter. So the 3 phases, again, we've listed them here: solid, liquid, gas. There are additional phases that are present in the universe. For example, a plasma is very common. The sun is a plasma. Fire is a plasma. Lightning strikes are plasma. You can apparently create plasmas in your microwave. I didn't know that. We're not going to really talk about plasmas that much in this class, but they exist. There are other phases that exist, like Bose-Einstein condensates, supercritical fluids, etc. We're not going to deal with any of those. We're just going to stick to the 3 basic ones because they encompass the vast majority of matter that we're going to encounter, and so that's really all that matters. Did it boom. All right, and then again, when matter interacts with other matter, chemistry occurs. Or chemistry does not occur, and both of those are important to us. We want to know what reactions are possible and what reactions do not occur, and then basically exploit all of those properties. All right. On this slide here, I have defined the 3 phases in terms of 2 different properties: shape that it occupies and volume that it occupies. Now, shape is going to be what 3-dimensional space does the object take up. For a solid, if I were to apply a force to this, not like a lot of force, like a small amount of force, its shape would be pretty rigid. It would not change, right? If you have a brick, for example, you could stand on a brick and it won't compress the brick at all. Concrete, for example, doesn't really compress or deform when you walk on it or push it or exert a force on it on any side. Some solids do this. So like paper, if you had a stack of paper and you blew a fan at it, its shape would change. But for the most part, the general shape of solids is fixed. If the shape of something is fixed, then its volume must also be fixed. So we can define a solid as anything that has a fixed shape and volume. With liquids, the shape is the shape of the container. So if this is my container right here, this is the shape of my liquid. But if this is say 20 milliliters, and I put it in a graduated cylinder that said 20 milliliters, then its shape would be this rectangle right here. So the shape changes even though the volume is fixed. Both are 20 milliliters. They take up the same amount of volume, but the shape of the space they occupy is unique based on the container they're in. And then finally, for a gas occupies the entirety of its container. So the gas is all of this space here. And if I were to open up the stopper, then the gas would evaporate and fill up the entire room. And then the room that the gas was in would be its space. So the shape of a gas is always changing based on the nature of the container it's in. So the shape is variable, and the volume is also variable. If I change the container, I change its volume. So if I were to actually compress this down so that I could make it just this tall, then the shape would be just this, and I could compress it even further if I wanted to. All right. So the space that matter occupies is known as its volume, which we defined earlier. And we know how to measure volume. We measure volume in milliliters, liters, etc. We're going to use SI units for this class. And so we'll just mostly measure in liters and milliliters, not gallons or cups or whatever. But mass is a little bit more obnoxious to conceptualize, particularly because as people who live in America, we don't use units of mass in our daily day-to-day lives. We use force. For instance, if you go and stand on a scale in your bathroom, it will tell you a weight in pounds. Pounds are not mass. Pounds are a force due to your mass times the acceleration of gravity. So the amount of mass something has is how much matter it contains. So that's this right here in yellow. But the weight of something is defined as that mass times the acceleration of gravity. And so you may have heard of this formula in a physics context. F equals ma. So acceleration. And this would be due to gravity. This right here is your weight, which is a force. The takeaway is that if you want to know how much matter something has, getting its weight is not satisfactory, because weight is subject to gravity, which changes depending on where you are. If you weigh yourself on the moon, you're going to have a different weight than if you weigh yourself on Earth. Likewise, if you weigh yourself in Death Valley, you might have a very slightly different weight than if you weighed yourself in, say, Nepal, somewhere with a really high elevation. Because gravity fluctuates depending on your distance from the center of the Earth, and also due to localized events such as just like turbulence in the mantle. Like if there's a particularly high density of iron floating around in the Earth's mantle under you, gravity would slightly increase probably. That's my best prediction. But down to a bunch of sig figs, like those numbers do change. We don't want to deal with that. So we divide out gravity and we just deal with mass. Now, the problem here is that when I ask you to determine the mass of something, I ask you to go weigh it. So be really mindful of just the language that is being used in this class with regards to matter and mass. And that language is, hey, I need you to find the mass of this. Go weigh it. Okay? You may hear people say, oh, you're going to go take the mass of it. Or go mass this balance, or whatever. But that's uncommon. Most people just say weigh, and the intent is you are going to get the mass of an object in grams or kilograms. Okay? Be mindful that you don't mix that up. Now, when we have matter undergo chemistry, the amount of matter that is present in a container doesn't change. what ends up happening is that if I mix a bunch of things together and they bonk into each other, they are allowed to react, and I create new products. But at no point do I discard or obliterate or transform into energy any of the matter that I'm working with. And so this is called the law of conservation of mass. And it states that the mass of the reactants and the products in a reaction must be equal. So whatever you put in is whatever you get out. And we can see that in this example here. If I make beer, the beer making process requires you to ferment stuff, but you don't do that in the open, because otherwise you would end up with flat beer, which nobody likes, right? So what we do is we cap the bottle. That's why I've highlighted this in green. This bottle is sealed, and so whatever is sealed in the bottle stays in the bottle. And I don't know what pre-beer is, because I don't brew beer. I know people who do, but I've never done it myself. I just drink the end product. These things are allowed to react with each other, and you create new things. So the sugar is fermented, and you get CO2, ethanol, and then all of the other stuff that was in the beer. All of those combine to give you the product that is consumed. Now, if you're in high school, replace the word beer with sparkling beverage or something. I don't know. So the hops was probably in this pre-beer mixture here. But you definitely need like some sort of yeast and some sort of food for the yeast too. All those things mixed together, and that's why it's fizzy. Now, because the bottle is sealed, the CO2, the carbonation that is produced by the reaction from the fermentation, can't get out. So there is CO2 up here that when you open the bottle, it'll go tss and come out. But if you were to weigh the bottle before and after the beer process was made, as long as it was sealed both times, you get the same mass. Now, this is interesting to us because some reactions do produce a gas, and if you can't seal a container, we can make that assumption that the gas is released and still determine information about it. So in this reaction, I have Alka-Seltzer tablets, so that's what this is right here. It makes CO2 bubbles, and those bubbles will eventually find their way to the surface, and the CO2 will escape. As you can see by this reaction down here. There's my CO2. Now, what we care about here is to figure out the conservation of mass. I could weigh the tablet and figure out its mass. I could weigh the entire cup, figure out its mass, then start the reaction, and then weigh the result. So let's suppose that I did that. So I'm going to take 10 grams of Alka-Seltzer and add it to 50 grams of water with a 0-gram cup, apparently. I don't know. And then I let the reaction occur, and then I put the thing back on the balance, and I get this number. How much CO2 was made? How would you determine that? How many sig figs would you write for your answer? Using the conservation of mass. Speaking of opening things with carbonation, let's get more seltzer water. Because I'm thirsty. So how many grams of CO2 must have been produced in the reaction with this data? There you go, very good. And how do you get that number? Well, if I have this many grams of Alka-Seltzer plus water, and I subtract out what was left after the reaction, the difference must be whatever escaped the container. And so I would have 2.1 grams of CO2 was observed. Now, our answer only goes to the 10th place because both of our values go to the 10th place. Make sure you're applying the subtraction rules. What different ways can matter interact with other matter? Here's just a bunch of different random observations that I've made. So maybe I can melt something by heating it. Maybe if I heat something else, it will scorch or burst into flames or whatever. If I drop something in a liquid, it may be recoverable. For example, if I put salt into water and then boil the water away, I get the salt back. But sometimes I'm not able to recover solids that way because they've reacted. And then all objects have properties that can be measured. These are all actions that I can take to things. Some of these actions actually change the nature of the material that we are looking at in detail. Others completely change. Others don't do anything to the matter at all. And so we're going to use this as our rubric. Does the matter change essentially irreversibly when we do X to it? If so, then the act of X is called chemistry. Otherwise, it's called physics. For example, if I throw a ball, it's still a ball before and after, right? So that would be physics. But if I throw the ball into the fireplace that is currently on fire, then the ball would burn, and it is no longer a ball. Like, it is chemically changed. That would be chemistry. That's more or less what we're doing here. We're going to distinguish properties of matter and changes in matter. For our purposes, these are going to be more or less just minutiae. We're going to examine qualities or actions and then just determine if physics or chemistry has occurred. But to be strict for our definitions, a property of any object is a quality that makes it different or unique. So, for example, a property of me would be I have a beard. That makes me unique compared to, say, somebody who doesn't have a beard. Another property of me would be I am 6 feet tall. That would make me different from, say, Maya, who is like 12 inches tall because she's a cat. Things like that. A change would be any action that causes a change. Like, duh, right? So, if I heat something, it may melt. That would be a change from solid to liquid. If I set something on fire, it will burn. That would be a change. If I put something in the freezer, its temperature is reduced, and so on. So let's look in a little bit more detail at how we understand whether something has undergone physics or chemistry. The rubric that we're going to use is we're going to look at the chemical formula. Now, that's a little bit difficult because what's the chemical formula for a rubber ball or paper or an aluminum can or ceramics? Like, what are the formulas for all of these things? And the answer to that is we're not really going to know them at the start, so it's kind of a shitty rubric. That said, we can use our intuition to identify whether something is transformed or not. In the observations lab, when you mixed multiple things together, if a chemical reaction happened, it was usually very obvious. You'd get a color change or a solid or whatever. I did grade those labs for this class, by the way, so those are done. I had to upload everything and then put the grades in the gradebook, but those have been done. So I know that everybody looked at the video and saw those differences and then recorded them in that table. If you take that sort of process for any sort of transformation, it should be fairly obvious if something is a chemical change. But strictly speaking, what we are going to use as our defining benchmark is what is the chemical formula before and what is the chemical formula after. There's supposed to be a straight line under it, but, you know, I did the best that I can. What is the chemical formula? These are things like oxygen is O2, water is H2O, nitrogen is N2, sugar is C6H12O6, like things like that. As you work with chemicals and develop more knowledge, you will just grow to know these formulas over time. All right. Let's look at a physical property. For example, melting of ice. When you melt water, or not melt water, I'm sorry, when you melt ice into water, what you end up with is a puddle. But that puddle can actually turn right back in a fairly easy manner, right? If you have water and you want it to turn back into ice, you just put it in the freezer. If you want something to melt, you just leave it out. If you want to boil something, you just put it on the stove. These are fairly easy things to do. Before and after the transformation, the formula of the substance remains the same. So what we would say is that, oh, melting ice is a physical change. For stuff that you don't know the formula of, that's where your intuition comes in. So, for example, if I take paper and tear it, even though I don't know what the formula is, I might be able to say, oh, it's like cellulose and stuff. But if I look at the paper that I tear and try and do the same things that I would normally do to paper, like, could I fold it? Yeah. Could I write on it? Yeah. Could I... what else do you do with paper, right? Fold it or write on it. So this must be a physical transformation too. What is this person doing to this paper? To be honest, I don't know. I think that they are making it look like it's old. So, like, they're trying to put a, like, jagged side on it. Maybe they're preparing for, like, Dungeons and Dragons or something. This is a scroll that they're going to give to their player. Alright. Now let's suppose we set the paper on fire. Is this something that we would call physics? If we consider before and after, from a formula perspective, we might not know what paper is. It's actually cellulose, so I'm going to write this. But after I burn it, I get CO2, I get ash, I actually get water vapor, etc. So, from the chemical formula perspective, this is obviously a chemical change. The formula has changed before and after. Excuse me. But if you didn't know the formula, perhaps you could infer this by looking at the properties before and after. If you start with paper and you end with ashes, do those two things compare at all? Can you write on a piece of paper like you write on ashes? No, you can't, right? Ashes are not paper. They don't have a surface. They're just charred stuff. You can write with ashes, but you can't write with paper. So these two are obviously different. And so the result that we end up with is that we've got a chemical change. The other rubric that you can use to determine if something is a chemical change or a physical change is the ease in which it is to transform the substance back. And so the way I show that, oops, my Photoshop didn't show up because I have to do that. So, depending on the ease of transformation that you can go in both directions of the process, will tell you if something could be physical or chemical. For example, if I start with ice, It's easy to turn ice into water. You just let it sit there. And it is not difficult to turn water into ice because you just put it in the freezer. You just lower its temperature, right? So if a change is relatively easy to reverse, then we are most likely looking at a physical change. That's supposed to be an arrow. But let's look at the paper and the fire example. This is very easy to do. You light it on fire and there it goes. But what about this? This is virtually impossible. My M kind of got messed up there, so we'll do that. So if one direction, generally the reverse direction, is just extremely difficult to do, then the transformation is chemical. For example, if you had iron and you let iron rust, that's easy to do. Iron will slowly rust over time. But can you unrust iron easily? And the answer is no, not really. And I don't mean like scrape the rust off. I mean take the actual rust and turn it back into iron. The only real way to do that is to do electrolysis or heat it or in the presence of carbon or stuff like that. That's difficult to do. So we can use this rubric as well to try and determine whether something is physical or chemical in nature. All right, so I'm going to put a bunch of these on the board here. Oh, after we talk about like why we care about chemical processes. This is a chemistry class, so we're going to look at chemical reactions all the time. When I write a chemical reaction on the board with an arrow here, we're basically just doing the shorthand version of this thing right here. So this is my chemical reaction. So here it is here. This arrow represents a transformation from reactants to products, and things are different on both sides of the arrow. I gotta go away. My cat is just very needy today. All right. So I'm going to give you all of these things. And what I want you to do is for each task that is listed, I want you to determine physical or chemical transformation. Once you've identified what it is, tell me what word specifically in that statement gave you the indication that, oh, this is physical or chemical. And then we're going to make some more generalizations after this. Okay? So go ahead and do this. Type your answers in the chat. We'll go over the answers together in just a moment. Another minute or two, and we'll go over the answers together. All right, let's go over the answers here. So for the first one, I am boiling water to make delicious pasta. When you boil something, you're changing its state from liquid to gas, but it's still H2O because you can take that steam and condense it back to water. So boiling water would be a physical change. For this second one, I am observing something to be purple. What that means is I look at it and I note that it's purple. If I look at something, does that change the something in any way? It shouldn't, right? So therefore, this is also a physical action. Hopefully not. Yeah, if it does, you should get your eyes checked at to see if you were emitting X-rays or something like that. Alka-Seltzer is dissolved in water, releasing a gas. Now, the key words here are actually these. Dissolving is kind of a dangerous word. Because if something dissolves, if you're Medusa, that Medusa definitely invokes chemical changes in people when she looks at them. So when something dissolves, it may or may not be recovered. So with Alka-Seltzer, if we try and recover the stuff, we can't because the CO2 has escaped. You would get something different out if you boiled away that water. But if you dissolve salt in water, you would be able to recover that. That would be very easy to do. So we can't really use the word dissolve because all dissolve does is change its state. But releasing a gas is a much better tell. Does water normally release a gas? No, not really, right? Does Alka-Seltzer normally release a gas? No, not really. What happens when you put them both together? Oh, it starts bubbling like crazy. So therefore, the act of putting those two things together is what causes the bubbling. And that must be a chemical change. What about sodium metal is melted? Well, we've talked about melting already. If melting ice is a physical change, melting sodium or any other metal or anything must also be a physical change, right? And yeah, it totally is. Melting is just turning something from a solid to a liquid. How about the gunpowder in a bullet being ignited? If you ignite something, you are setting it on fire. Typically, you can only set something on fire once. Once you've done that, you've already turned it into a product that doesn't have any potential energy in it anymore. So, this must be chemical. What happens if you compress something? Compression is just taking an object and making it exist in a smaller space, right? Well, if you take air and compress it, all that does is make it be air, just with a higher pressure. It's in a tinier space. It's still air. Its formula is didn't change with the substances that were in it. If you whittle something, I just wanted people to say the word whittle. You're basically chopping it into smaller pieces. Well, wood is still wood, regardless of whether it is a giant log or a small sculpture of a chipmunk. I actually have a woodworker in my family. My grandmother's sister. I don't know if she's alive, but she would make all these little, like, forest critters out of woodwork, and they were really cool. So I had, like, a room full of them. And I kind of wish I still had them, because they were really neat. But this is definitely physical. And then finally, gasoline's combusted in motorcycle energy. When you combust something, you're igniting it. You're setting it on fire, right? Can't recover that very easily. Otherwise, gasoline would be reusable, and that'd be awesome. But once you combust the gasoline, it's very hard to get gasoline again. What are we going to do when we run out of gasoline? I don't know. We're not going to have cars anymore, I guess. I mean, we'll have electric cars, sure, but... All right. There are the answers. Let me know if you have any questions. And let's talk a little bit about some other properties that we can measure. I'm going to use the terms intensive and extensive to describe certain things in this class. An extensive property asks you how much stuff you have, but an intensive property does not. So, for example, if I asked you to determine the mass of water in a container that I give you, and I give you a gallon of water, and I give your lab partner a cup of water, which one has more mass? That should be really obvious. The one that you gave the bigger container to, right? But then let's suppose I asked, which person has water with a higher density? I gave you more water, so you have more mass, but I also gave you more volume, so those two divide out. Both people have the same density of water, regardless of how much water I give them. So I would say that a property like mass would be extensive. The more you have, the more its mass is. I can't click on the darn pen. There we go. But something like density would be intensive. I can give you all the water you want. Its density will still be 1 gram per milliliter, or roughly that. And so you can go through these examples. I'll leave these out for you. I want you to tell me which are extensive and which are intensive. I'm going to go figure out my cat is destroying the bathroom. Sigh. So type your answers in the chat, and we'll go over the answer in just a second. Oh, I think my cats are just bored. They want to go outside, but it's too cold to open the door and let them out. All right. Once you know which ones are intensive and which ones are extensive, type them in the chat, and we'll go over the answers. All right, let's review. So, if I give you more of something, do I increase its volume? I'm just going to pick, we're going to pick gasoline for this example. So if you have more gas, does the volume increase? Yeah, so that would be extensive. If I give you more gas, is it more flammable? Gasoline is flammable whether you have a little bit of it or a lot of it, so this would be intensive. If I give you more gas, does its boiling point increase? Well, if we don't know the boiling point of gasoline, we could look at the boiling point of water. If I give you more water, does its boiling point increase or change? No, water boils at 100 degrees regardless, right? So, boiling point must also be intensive. Mass we already talked about. And then state, if I give you more matter, does it change state? If I give you more water, would it suddenly become a solid or a gas? No, those aren't related to the amount at all, right? So that would be intensive as well. All right, so there's our answers. Let me know if you have any questions about intensive versus extensive. All right, I think that's the end of this section. It is. Okay, so when we come back from the break, we're going to go over pure substances and mixtures. Explain the last one. Sure. So if I give you more stuff, so like say, I don't know, here's 100 milliliters of water, and then I add that to another container, and I keep doing that until I have 100 liters of water. In both cases, they are still liquid. So the state of the substance does not change based on how much is present. Because I could give you a small amount of liquid, like a little teacup, or I could point at the ocean. The ocean is very, very, very large in volume. But regardless of how much water I have, it's still water. So I would say that state is an intensive condition. It does not depend on how much stuff you have. It would depend on other things, such as temperature, pressure, etc., but not amount of matter. All right, so let's go to the break card. We will take a 10-minute break. I'll put some more Earthbound music on, and I will see you in just a little bit. So go fill up your water, and we'll be right back. All right. Let's fade the music out here. We'll click over here, and we'll get back to it. Let's do the rest of chapter 6 today. So now that we've talked about physical and chemical transformations, let's try and categorize matter in a different way. Let's talk about what it's made of, and see if we can categorize it based on that. On the screen here, I have a cup that contains presumably water, and a cake, which contains deliciousness. If I had to assign the word pure to one of these two things, which one would be most likely the candidate? Which is most likely to be pure? Yeah, water, right? If you know where you can find pure cake, let me know, because asking for a friend. If the substance that you're looking at contains only one chemical formula in it, so only one thing, then we say it's pure. If something has many things in it, then we say it's a mixture. So an object can either be a pure substance or a mixture. It cannot be both. And that is going to entirely depend on the number of substances that are present with regards to their chemical formula. Now, this is obviously not a perfect way to discriminate from one substance versus another, because you could end up in a situation where, say, like ice water. Is ice water pure or a mixture? By our definition, that would be pure, because it's got H2O as a solid and H2O as a liquid, but only one type of compound. All right. So that's what we're going to look at. We're going to look at, is there one substance present? So one formula. If the answer is yes, we're looking at a pure substance. If the answer is no, we're looking at a mixture. Let's look at pure substances in more detail and assess what their chemical formulas can be. I'm going to give two examples here. I'm going to give diamond and table salt. A diamond contains only one element, and that element is carbon. Diamond is entirely carbon. If you have a periodic table handy, and you can look up the components that make up your matter, your pure matter, and you only find one element on the periodic table, we're going to call that substance just an element. Likewise, if you can find two or more elements on the periodic table, such as in table salt, which has Na and Cl in it, sodium and chlorine, we're going to call that a compound. Compounds have two or more types of elements in them, whereas an element has only one element in it. Some interesting facts about elements is that you can't break an element down. Elements are as simple as they can get. That's why they're called elements. Whereas a compound can be broken into simpler substances. Usually those simpler substances are elements. So you can turn sodium chloride and table salt into just pure sodium and pure chlorine. The table salt itself is still pure because it's the only thing in the salt shaker. So those are two categories that we can use to discern between elements and compounds, the two different types of pure substances we're going to care about. What about for mixtures? On the screen, I have two different mixtures here. I got ketchup, which is something that you put on fries, and salad dressing, which is something you don't put on fries. But putting things on fries is probably not the best rubric. What we're going to do instead is we're going to take the sample, and I'm going to just circle random parts of it. So this part, this part, this part, and then over here I'm going to circle that, that, and that. If a mixture can be separated into parts such that all of the parts are indistinguishable from one another. For example, if I have ketchup and I shake the ketchup bottle really well, and then I squirt ketchup into 4 little cups, would all the cups have the same flavor, appearance, texture, etc.? Typically, since you mix the ketchup really well, the answer to that would be yes. We're going to consider that to be a homogeneous mixture. A homogeneous mixture is consistently the same throughout the entire substance. All portions you take are the same. They cannot be discerned by our eye or senses or whatever. Down here, though, on the salad dressing, on top here I have mostly oil. Over here I have mostly herbs. And then down here I have mostly the insoluble good stuff. So yum. Those are all very different. At the top I get way more oil than if I take from the bottom. So if I did not mix my salad dressing, I would not get the stuff at the bottom if I poured from the top. And then the later samples that I took from it would be very, very different because all that concentrated stuff would be at the bottom. But even if I did mix the salad dressing, it still tends to separate after a while, right? We're going to say that in the current state that I see the salad dressing on the screen here, we're going to call it a heterogeneous mixture. Heterogeneous mixtures have different portions throughout. Now, there is obviously some leeway here, and it might be difficult to discern, like, okay, well, where's the dividing line? So, for example, would milk be homogeneous or heterogeneous? Well, if it's like skim milk, then it's homogeneous, or if you shake it, it's homogeneous. But if you allow, like, the whey to be separated from the curds, then those are two different substances, and therefore they would have been heterogeneous. So you can make that argument for almost everything. What we're going to do is we're going to try and keep it simple. I'm going to give you a situation that I feel like should be easily described, like muddy water, or wet sand, or poorly mixed gravel, or soil that you would dig up from the ground. Like, these are all examples of things that are just fairly commonly considered mixtures. And the answer to all of those should be fairly obvious. Things that tend to be solid should generally be heterogeneous mixtures. Like dirt, for example, would be a heterogeneous mixture. There's no guarantee that if you shovel up just random piles of dirt, you're going to get the same stuff in every shovelful. Like, there might be more pebbles in one scoop than the other. Most foods are going to end up being heterogeneous. So, like pizza, not every slice of pizza is identical. Not every bite of pizza is identical. If you eat from the crust end, it's different from eating from the center end. Cereal would be heterogeneous because not every bite would have the same amount of raisins or corn bran or Lucky Charms or whatever it is that you eat. I don't know. I don't eat cereal. All right. So there's our complete flowchart. And using this flowchart is useful for discerning what category stuff falls into. Now, keep in mind, you have to follow the flowchart. So something cannot be a pure substance and a homogeneous mixture. Like, that's not possible because they don't connect. So you cannot assign those two properties to each other. But something could be a pure substance and a compound. You're just going to follow the chart. On the next slide, I have an example of different substances and what categories they fall into. You can pause the video if you want to look at that. And then I have the examples. So I'm going to give you these substances. I want you to tell me which category do they fall into. So pure substance or mixture. And then which subcategory of those two categories they fall into. Element, compound, homogeneous, or heterogeneous mixture. Okay. For the substances that are listed, for example, Red Bull energy drink, consider the ingredients on its label. But nail polish remover, I have listed the only ingredients. Okay. So if I don't list the ingredients, you can make an assumption based on what you know. But if I list ingredients, that's what's in there. Okay. So that's what the parentheses mean. With one exception, down here, tell me which pizza parlor is your favorite. That is part of the assignment. So type your answers along with your favorite pizzeria in the chat when you're done. We'll go over the answers when we're ready. All right, 1 or 2 more minutes and we'll go over the answers. All right, let's go over the answers here. So I got Red Bull. Looking at the ingredients on Red Bull, you can easily determine, oh, there's more than one ingredient. It must be a mixture, right? Hold on, cats. Nope. Nope. Maya has visited me no less than 6 times today, and that is about 4 times too many. All right. Is it homogeneous or heterogeneous? Okay, well, if you open up Red Bull and you pour the contents, and I realize you don't have that much, into, like, say, 2 glasses, would the 2 glasses be the same? And the answer to that should be yes. So Red Bull should be a homogeneous mixture. Most beverages are homogeneous mixtures. And the reason for that is because you want every sample from the container to be the same. You want the tasting experience to be the same every time. Now, whether they go flat or not is a different story, but they're still homogeneous whether they're flat or not, because the CO2 dissolves out evenly. All right. Nail polish remover. In the container, remember when I have parentheses, this is the only thing that's in there. In the container is acetone, which has this formula, because you probably don't know the formula of acetone yet. That's fine. So there's only one thing present, so it's going to be a pure substance. Not per. Cat on the brain, I guess. Here. So pure substance. And the substance that's in there has many, many elements. So this is going to be a compound. All right, poorly mixed gravel, and the gravel contains these things. Well, there's multiple things, so this is a mixture. And I told you that it was poorly mixed, so it must be heterogeneous. For the next one, I have nitrogen gas. What is nitrogen? Well, it's just N on the periodic table, right? So, there you go. Note that nitrogen gas is not air. Air would be a homogeneous mixture, but nitrogen gas is just nitrogen gas. It's just nitrogen. All right. Any pizza and really any food is going to be a mixture. And every bite of pizza is different. So we're going to say heterogeneous. Now, what pizzerias do we have out here? I see Brooklyn Brothers. What other pizza places are good? I want to know. Heterogeneous and homogeneous only apply to mixtures because on our table here, I can only get these things if I was a mixture to begin with, right? So you cannot have a pure substance that is also a mixture. All right. What other pizzerias are there out there? Only like 1 or 2 people answered my question. Which is too bad. Nobody gave me the correct answer. Which was Zeke's Pizza. Zeke's Pizza was the correct answer. Sahara Pizza. I've never heard of that one. I'll give that one a buzzer too. I do like the cowboy from Papa Murphy's. It's a little greasy though, for some reason. Like it shouldn't be, but it is sometimes. Iron metal, all I listed was iron, so it must be pure iron. And then you have to find iron. Is it on the periodic table? It is. That's an element. Element. There we go. Coconut Kenny's. I've never heard of any of these. Generally, like, if I have not heard of a pizzeria, that means that it's probably a small chain and it's probably good. Well, it's either very good or very bad. And usually the bad pizzerias don't last very long, so. Like, most of the chains of pizza are not that great. Mod Pizza is okay. Like, I'm not a big fan of Mod Pizza, but it's not awful. It's not like Pizza Hut or Little Caesars, heaven forbid. Papa Murphy's is probably the best of the chains. I don't really call Zeke's a chain, but it really is because there are like 5 or 6 of them. Zeke's Pizza is amazing. I like any crust. Generally speaking, I like thick crust. But I won't say no to a thin crust pizza. I also won't say no to a deep dish pizza. Although we don't really do that over here. That's more of a Chicago, New York thing. I have friends who live in like Boston that are like, oh, you have to try our deep dish pizza. I'm like, we don't ever have that over here. Down here, steel. Steel's actually a very important example here. And this is one that everybody gets wrong. Steel is obviously not a pure substance because you put a bunch of stuff in there, right? But maybe it could be a pure substance because it has a formula. Well, think about how steel is made. Steel is made by heating up a lot of stuff and then causing it to cool in a like mold or something, right? So you put in your iron, you put in your charcoal, you put in your other elements, nickel, manganese, chromium, vanadium, whatever. And then you mix, and then it cools down. Now, if it was molten at the time, everybody would probably say, oh, I threw all this stuff in there and then mixed it together. It's probably a mixture, and that's correct. Steel is a mixture even when it's cool. There is no formula for steel. It is just a bunch of atoms conglomerated together. But what type of mixture is it? Well, if it was heterogeneous, then that would mean that not all of the steel was made the same during the process, which would be a real problem for, like, manufacturing. Oh, we made steel, but don't use the left end of the bar. That end's weak. Like, no, that's not going to happen. All steel should be the same. So, steel is a mixture and is a homogeneous mixture at that. It is not a compound because there's no formula to it. There's no chemical formula for steel. Because of how it's made, you put all of the components into a furnace and you heat them up until they're liquid and then you mix them together. Now, this specifically is called an alloy. An alloy is any combination of metals that you obtain by forging. And all alloys are homogeneous mixtures. Okay? Important to know. You're going to see alloys on the quiz, which is going to get released tonight. All right, let me know if you have any questions. The last little bit of Chapter 6 is just sort of a symbology lecture. Like, there's like only 4 or 5 slides, so we're almost done for today. And it's really just an introduction to, here's how we're going to represent stuff in this class. We're going to use symbols. Now, there is a video that I would love to show, but I guarantee I will get copyright striked for it. So what I'm going to do is I'm going to link it in here. So you may have seen the video History of the World, I think. And so, I gotta hit mute on this. Although I am gonna, when you hear this,
I miss you.
How did this happen?
like, you immediately know what that video is, right? And so, if you have seen it, so I'm gonna paste the link in here. And so, the relevant part of this video is really only up until, let's see here. It's up until it's a star. The first 2 minutes. So the first 2 minutes are actually physics and chemistry. After that's a little bit of biology, and it keeps going, and it's really funny, and it's 20 minutes long. So I'm not going to sit here and watch the whole thing with you guys. But if you've never seen, you can absolutely trust this. It is this video right here. Which didn't appear. There we go. So, History of the World, I guess, by Bill Wirtz. Bill Wirtz does all sorts of crazy music. You may have seen this video before, or, like, have seen references to it. Like, I'm just clicking through it because I don't want to, I don't want some censor to go, oh, you're not allowed to show that on here, and then get the videos, my video scrubbed. I have no idea if Bill Wirtz monetizes this, but he has 4.5 million subscribers, and this video has been viewed 111 million times. So, I'm very reluctant to put such a popular video on my teaching stream, because then this specific lecture will just go poof if it gets copyright struck. So, why do I bring up that video? Because in the video talks about how at the beginning of the universe, the only elements that were present were hydrogen. Maybe a little bit of helium. When all of the protons and electrons and neutrons coalesced together after the Big Bang. What ended up happening is all of that then conglomerated into a star. And then when the star produced energy, it would combine hydrogen into helium and then helium into other heavier elements and so on and so forth until the star ran out of fuel and blew up. And that's where all of the other elements come from. So about 91% of matter in the universe is hydrogen. Yeah, that guy made a lot of money off of that video, and that's why I don't want to get copyright struck on it. So I don't want to play that on here, but you should watch that video, if only for the, wow, this is really funny, and also, wow, there's a lot of interesting stuff. But the takeaway is that almost all matter in the universe is hydrogen. There is so much matter out there that it's almost entirely hydrogen. About 9% is helium, and then the rest, which you can't even see on this bar graph, is oxygen, carbon, and then so on and so forth. And then this is everything else from there. I think that there was a third graph which blew this up and showed what that tiny percentage was of everything else. Suffice it to say, we are made primarily of... Oops, there's no check mark there because it's also red. We are made primarily of those three and this one. So there's a lot of matter in the universe. And it is constantly being upscaled to more and more complex matter, as in it has more stuff in it. Now, specifically speaking, the data that I have here is for the sun, so the universe is similar to this. It's not exactly like this. There are many stars that have already exploded. The sun is not going to go supernova anytime soon. If it was, it would be much less hydrogen and much more helium and iron and other heavier elements. But those heavier elements do exist in the sun. For example, there is more gold in the sun than there is the entire mass of the Earth. We should go mining on the sun for gold. I mean, if you could figure out how to do that, you'd make all the money ever. Time to mine the sun. All right. How do we represent all the elements? We do it symbolically. The reference that I'm going to give you is this one. There you go. Let me make sure that I linked that correctly. Yep, there we go. So this is p-table. P-table is a periodic table and also just information database for all the different elements. You could click on any element and learn about it. Like it'll pop up like its characteristics, melting and boiling point, etc., stuff like that. Virtually all of this information will be relevant to you at some point throughout the Chemistry 140, 161, 162, 163 series. Maybe not the materials properties, so like you don't need to know its thermal conductivity or its shear modulus or Mohs scale. Although if you're a geologist, that's interesting. Like that's interesting to me. I almost sat there and started reading it. Like, oh, I'm teaching, I can't do that. But for each of these elements, you're going to see that there is an associated symbol. And that symbol is like a 1 or 2 letter code. It's important that these symbols are interpreted as shown on the periodic table. What that means is that if you were to write something like this for xenon, where you, I don't know, if you like, I write like this, where you write in what I call lower caps. If you do that with a symbol, wrong, wrong, so wrong. Okay? This is a symbol, even though it's made of letters that we represent, in the same way that this is a symbol, and if I translated it to this, these are different. Just like this and this are not the same. Okay? So whenever you're writing out symbols, make sure that you are using the first letter as a capital and the second letter as lowercase, always, always, always. Otherwise it gets marked wrong, and that's no good. All right, let's clear all this off the screen here. Oops, that's not what I wanted to clear. Oop, there we go. Now, where do the names come from? Generally speaking, most of the names came from, oh, we named it and then we made a symbol off the name. Now, some of those names that were given to civilizations that were very early. So, in prehistory, elements were known. For example, iron was known. And so the Latin word for iron is ferrum, and so the symbol for it is Fe, because it was just so ubiquitous. And also other societies who their languages are derived from Latin have terms that are similar to ferrum for iron, for example. So like Spanish and Portuguese and French and Italian, all of those are Romance languages that are based off of Latin. And so the word for iron in those languages is probably very similar to ferrum. And so those societies, when devising element names, they probably just decided, okay, that's the symbol we're going to go with. And the rest of the world was like, yep, there we go. Capital K is for both potassium and Kelvin, so just be careful. One is an element, one is a unit. W is technically the unit for watts, but it is also the element for tungsten, which is Wolfram in German because they found it first. So you're obviously not going to have to memorize the periodic table because you're going to have p-table handy. And so you can always go to p-table to recognize where these elements are on the periodic table. You might do some hunting. What I want you to do, though, is as you are using the periodic table, be on the lookout for pairs of elements, such as, say, this one and this one. Or, example, this one or this one, that have names with weird symbols, usually due to Latin prefixes. For example, tin. Tin is not Ti. Ti is titanium. Tin is actually Sn for stannum. P is not potassium. P is for phosphorus. Potassium is actually K because K is calcium. Calcium being Latin for potassium. And there are all sorts of examples all across the periodic table. I can't tell you the number of times the letter C appears on the periodic table. I mean, we could try and circle it. Like, there's carbon, there's Ca for calcium, there's Cs for cesium, Cr for chromium, Co for copper, or cobalt, Cu for yeah. See, even I'm getting them mixed up. Cu for copper, Cl for chlorine, Ce for cerium, Cm for curium, californium is somewhere. There it is. Like, holy crap, if you just look for C, cadmium, I forgot cadmium, there it is. Like, there's a lot of C elements on there, so be very careful that you're clear about those, because the naming convention is not always clear. For example, there's an H in chlorine. You probably weren't aware of that unless you've ever bothered to spell it out. But we use Cl for its symbol and not Ch. So the symbol is just whatever we decided it was going to be. So be on the lookout for those places, because those are easily ways that can be roadblocks for people trying to write out elements correctly. Another issue that people run into, and I want to clarify this one right here, is a lot of people see Cl and think that this is actually carbon and iodine. This is never, ever, ever the case. Okay, so if you ever see Cl, this is chlorine. So, for example, if you see HCl, that is not HCI, that is HCl. Okay, so never write HCI on anything. It doesn't exist. Some texts will try and take L's and do this with them, to be clear. But not all texts do that. Aluminum is another good example. Aluminum is always Al. There is no element A by itself, so you can't have AI. On the periodic table. You can have AI in other contexts, obviously, like artificial intelligence. But so just be mindful if the second letter is L. That is a possibility. I think that only happens for chlorine and aluminum. I'm actually looking now to see if there are any others that have a second letter of L. And I don't see... Oh, thallium, but we never even touched thallium. Thallium is... I don't know what thallium is for, other than it's toxic, probably. All right. This is just a little bit more about formulas. Any formula will tell you the components that are within its molecule. We're going to talk a little bit more about molecules in the next chapter. But if I have a water molecule and its formula is H2O, that would tell me that there are 2 H's and 1 O in a water molecule. If I wanted an ammonia molecule, and I know that ammonia has 1 nitrogen and 3 hydrogens in it, then I would write NH3 as its formula. Notice that for any element that there's only one of, you do not write a 1 for it. You just write the letter or letters for the element without a subscript. Element numbers are subscripts, which means that if I have 7 of something, there would be a 7 in the subscript. I can put any number I want in a subscript. It must be an integer. So I cannot write a formula like this. That does not make sense because 2.5 is not an integer. All right. We've already talked about lower caps. Do not do that. And then, if you remember those polyatomic ions that we showed at the start of the class, polyatomic ions stick together. And so if you see them in compounds, they will oftentimes have parentheses written around them like this. This is written as wrong because we lose information here. This just says there are 2 O's and 2 H's. Whereas this tells us there are 2 OH groups. So sometimes you will use parentheses in a formula to keep a common group together. So just be mindful that that is a thing that can come up and will come up when we talk about ionic compounds in chapter, I want to say 9, in unit 9. Alright, so I have this example, but this is really just you counting elements. So, like, can you count the number of carbons? Of course you can. It's right there. It's 18, right? That gets more difficult down here. Because I'm going to just do these examples with you instead of you doing them. When I'm counting elements with parentheses, what this means is that I have 6 of these groups altogether. So if I want to write all of them out here. I forgot a phosphorus there. Alright. So if I have 6 of those groups and I said, how many phosphorus are inside there? You would say, oh, well, there's 1 in each group. So 6 times 1 is 6. And then if I asked you how many oxygen are in there, you would say, oh, well, there's 4 in each group and there are 6 groups. 6 times 4 would be 24. And so there you go. So there are 24 oxygens in just this phosphorus part. So this 6 and this 4 multiply together. If I asked you how many oxygens were in hydroxyapatite, you'd have to include these oxygens as well. So in hydroxyapatite, there would be 10 calcium, not 4. I looked at the wrong number when I was thinking that. 6 phosphorus, 24 plus 2 oxygen, and 2 hydrogen. So be mindful of parentheses in formulas and what they are trying to tell you, because that will come up from time to time too. All right. Any questions? I think that that's it for the chapter, because there's only like 30 slides in this. Yeah, that was the last slide. So if you have any questions, let me know. Here is your victory orb. Hooray. On the next quiz, if there is math, there will be sig figs. Sig figs never go away. So if you have any mathematics on the quiz, and I believe that there is, because quiz number 3 is density, and I don't even bother asking it. If there are numbers involved, do your sig figs. There will never be a time where I say, oh, it's okay to ignore sig figs. This is your life for the rest of chemistry. But no, seriously, like, sig figs are important. Okay, that's all I got. So, we're out of here 15 minutes early? Sweet. If you have any questions about anything from units 4, 5, or 6, let me know. There is going to be a quiz on these that I am going to post right now. Tomorrow is a lab lecture, so we're going to go over lab worksheet number 2, and also have a Q&A. If you have any questions, please bring them to the Q&A. We can go over them then. Otherwise, I just want to thank everybody for coming out to the lecture. I will see you tomorrow for that lab lecture. Have a good night, and we'll see you then.